This meeting is being recorded.
Okay, I think everything is being recorded now. Hopefully you can hear me. Hopefully you can see my slideshow. If someone could just type in the chat that you can see the slideshow and hear me, that will be great. Okay, many thanks. Many thanks. So, welcome then to this tutorial on Arcuda, which stands from Remote CUDA. This tutorial is entitled Over a Decade Offering Remote GPU Virtualization Services. Actually, Arcuda started on 2008 and I joined the team on 2011. So it's been over a decade also for me. So this is the tentative schedule. So we will have different parts, more related to theory in the beginning, and then more related to hands-on in the last part of the tutorial. We plan to do regular coffee breaks. Every hour we plan to have a coffee break of around 15 minutes. And I will start then the tutorial with the first part. And yes, while I'm speaking, if you have any question, please don't hesitate in asking the question. You can use the chat or just your voice, whatever you prefer. That's fine for me. Okay, so let me check if I can now share the other slideshow. Okay, so what is actually Arcuda or Remote CUDA, and how to use Arcuda? So we will see the basics of Arcuda during this talk, and we will also see some measurements in terms of performance and things like that. So, as you probably know, currently we need a lot of computation power in order to make applications run. This applies to applications doing, for instance, DNA sequencing or fluid dynamics, weather forecasting. So and what happens is that those applications require a lot of computing resources. They have a huge execution time, and so for that reason we want to accelerate those applications. One way of accelerating these applications is using graphic processing units, GPUs. And for that reason, GPUs started to be used for accelerating applications, and currently they has actually consolidated as we could say the accelerating technology. Okay. So usually what we have is a node, a server with one or more GPUs. And in this case, we can see here in the slide a server with 4 GPUs. And this is what we can call like the basic building block in a high performance computing cluster. And we will have typically more one or several of these nodes in one cluster in order to make a computing facility accelerated by GPUs. So when we want to accelerate an application using a GPU, what we usually have is we have one of these nodes. In this case, in the slide, we can see a node which has different GPUs. So then we have an application which is running, and when this application requires GPU acceleration, when this application requires being accelerated by a GPU, if we are using an NVIDIA GPU, we can make use of what is called CUDA, which is an extension of C language in order to accelerate this application. This is what we refer to as the basic behavior of CUDA. For instance, if we are using the version of CUDA for C, C++, what we need to do in order to accelerate our program is basically we need to include the CUDA libraries, which are marked in the slide in red. And then we just need to declare the functions which will be accelerated in the GPU. This code is in Glean. For instance, here we have a function called my GPU function. This function will be run in the GPU. Then in the main part of my program, I need to do the same things I usually do for running an application in the CPU, but in this time we need to do this for the GPU. This includes allocating memory in the GPU. This includes copying memory from the host memory to the GPU memory. This includes running actually this function or calling this function in the GPU. And finally, we need to copy the results back to the host memory. So we need to copy from the GPU memory to the host memory. And in the end, we also need, in the same way we do with a regular program, we need to free the GPU memory. Okay, so this will be the basics of a GPU accelerated application. So once we have this basic building block, which is one node with GPUs, we find that at the cluster level, we have heterogeneous clusters, which means that some of them of the nodes in this cluster has CPUs with several cores per CPU, of course. Then some of these nodes could have GPUs, but not all of them. Typically, the number of GPUs per node used to be between 1 and 4, but now I would say that this number is going to 8 GPUs per node. And all of these nodes are connected in the cluster by an interconnection network. So the problem, one concern here of having these heterogeneous clusters is that if we want to run an application accelerated by GPU, we can only use the nodes in this cluster which has GPUs. Okay. We cannot run a GPU accelerated application in a node in this heterogeneous cluster, which only has CPUs. So when we have GPUs across all the cluster, like in this figure in which we represent the interconnection network in the bottom, then we have different nodes, and in this case all the nodes are similar. We have a couple of CPUs and then one GPU per node. So in this case we can run an application in one node, but notice that an application running in node 1 is not sharing anything with an application running, let's say, in node 3. So for this, something else will be required if we want to share resources For instance, we can use MPI in order to aggregate resources and to run tasks that collaborate while running in different nodes. Okay, so of course, we could say that the GPUs and the acceleration they provide enable progress because they accelerate those applications. They reduce tremendously the execution time, and that's a very good outcome. But we have sometimes we have different concerns because those GPUs are usually very expensive. Those GPUs usually are very power hungry. They consume a lot of power, and usually one application is not using the GPU all the time. So this means that the GPU utilization is usually low. GPUs are usually underutilized, and this means also that the power consumed by a GPU, even when they are idle, they are consuming power. So we are wasting energy. So as we have mentioned, we have very expensive devices which consume a lot of energy and that are underutilized. Okay, so on the good side, we have they provide a huge acceleration, and on the bad side, we could say that sometimes we have these concerns. Let me elaborate a bit more on these concerns. For instance, here in the screen, we are showing the measurements related to the execution of an application which is called GPU Blast, which is just doing DNA sequencing. So in this case, we can see the red in the top of the slide. We have the memory and the GPU utilization. In terms of the GPU memory, we can see it in the gray bars. In terms of GPU utilization, we can see it in the red lines, and the average utilization, GPU utilization, is marked with the is shown with the dashed blue line. So as we can see, at the beginning, we use the GPU from time 0 to 10 seconds. Then the GPU is not used until time 35 or so. Then we use it 10 seconds. Then we have it again. We are not using it again during a while, and then we use it again. So as you could see here, we are using the GPU during some periods, but for the rest of the application, the GPU is not used. Although it is not used, the memory, the GPU memory allocated for that application is still there. And as you could see, the average GPU utilization in this case is very low, is below 30%. Okay. In terms of power, of GPU power, of power consumption, we could see that when the GPU is actually being used, is making computations, we have almost 80 watts of GPU power. And then when we don't use it, when the GPU is idle, because let's say the CPU is doing some work, we see that we still have over 30 watts of GPU consumption. Okay, so the average GPU consumption is actually over 45 watts. And this highlights what we were mentioning in the beginning, saying that even when we don't use the GPU, we are consuming energy. So, well, as I have mentioned, we have times here in which the GPU is assigned but not used. And we have already mentioned also this, that during the periods in which the GPU is assigned but not used, the energy is still being consumed. So Well, I think we have already mentioned things, everything like this. We have. Let me show you another application. So the previous one was GPU last. This one is Cloverleaf. So in this case, this is a good case because the GPU is always being used. We have almost 100% of GPU utilization. So here we are consuming energy, but the GPU is being used, so we don't have underutilization, and this is like a good, the desired case, right? So we have we are using the GPU almost all the time, and in this case, this is the good scenario. But as mentioned, it is not always possible. There will be applications which cannot use the GPU during all the time. So let me show you now, for instance, if we come back to the case in which the GPU was not used all the time. So one could think, okay, what if we could, while this, when we are actually not using the GPU in this time, what if we share this GPU with other applications? For instance, if we were able to run 3 instances of the same application, we could run these applications concurrently. They will use the GPU in a sequential way, and with this, we will increase the GPU utilization. Okay. So this seems a good approach in order to address this concern. Okay, if we have a GPU underutilized, we share that GPU between multiple concurrent applications. So this is actually what we have done here. In this case, we have run different applications. So you can see them in this in the slide. We have run an application called LAMPS, an application called CUDA-Mimi, another application called Barracuda, etc. So we have 5 applications, and what we have done is we have run this application only once, and we have measure the time, and then we have normalized this time, is what you can see in the black bar. So here then we have run the same application twice, and so here we can see that we have run the application twice, but the execution time has not doubled. Okay. And when we run it 4 times, in this case, for instance, for the LAMPS application, so the time for 4 instances is only twice the time of 1 instance. So this makes us think that it's maybe a good idea for some applications sharing the GPU. In this case, all the applications we show here, it seems a good idea to share the GPU. Okay, notice that in some cases, for instance, for the Barracuda or the Mamba GPU, it was not possible to run all the instances because, of course, the limitation here is the GPU memory. In this case, we had only 5 gigs of memory in this GPU, so this will be the limitation. Okay, for instance, the Mamba GPU, it needs 2 gigs, so if we want to run 2 applications concurrently, it's okay, they can fit. The 4 gigs can fit in the GPU, but when we want to run the 4th instance or the 3 or 4 instances, we will need 6 or 8 gigs in memory that in this case we don't have. Okay. So as mentioned, we have also already mentioned that the main concern here is for sharing the GPU is the GPU memory. Yeah, we should also notice that we were doing these experiments with a very old GPU, the K20, but right now current GPUs, they have a high amount of memory. For instance, the A100 GPU has 40 gigs of memory. Okay, so maybe with this the new GPUs, these limitations in terms of memory are removed. Okay, so how can we share a GPU efficiently? We have seen that in some cases it could be a good idea to share a GPU. So how can we do this? So the first option will be, okay, let's directly share the GPU among the concurrent applications without any hardware or any software orchestrating that share. Okay, that will be a bit difficult, right? Because we will just run our application. If there is enough memory, it will run okay. But if not, it will just fail. And who has a priority? Which application has priority for using the GPU? Things like that. Okay, it seems not a very good idea not having anything, either hardware or software, in order to orchestrate or to support this sharing. The second option will be having some support from hardware or software to share the GPU, to efficiently share the GPU between different applications. This is exactly what we are trying to explain in this workshop. So it's providing something to virtualize the GPU. Okay, some support in order to offer these GPUs shared to all the applications, and properly managing the GPU sharing. So then, after this brief introduction, what is actually Arcuda? Okay, Arcuda. Well, before we explain what is Arcuda, perhaps we should explain what is remote GPU virtualization. So, of course, it is related with GPUs. As we have mentioned in the beginning, we have usually in clusters, we have servers with GPUs. And we have also explained that the basic behavior is that I have an application running on a node which has one or more GPUs. So when this application wants to use the GPU, it just uses, for instance, libraries provided by NVIDIA, the CUDA libraries, and the application can be accelerated with the GPU. We have already explained this, and we have seen that this is the basic behavior. Okay, what happens if we are using remote GPU virtualization? That we actually do not have a physical GPU. So we can have the application, we can use the CUDA libraries, but when we want actually to accelerate this code using the hardware, we don't have such hardware because we are virtualizing it, okay? So when we mention remote GPU virtualization, what we actually are referring to is, okay, let's say we have a cluster with no GPUs, and then when those clusters are running GPU accelerated applications, we just intercept the calls to the GPUs and forward them to the remote GPU servers through the network. And with this approach, we will be able to run GPU applications in nodes of the server, which actually does not have actually do not have a GPU installed. So here we can see that we have in every of these nodes different applications, and they are able to use remote GPUs. So notice that one or more GPUs can be shared by one or more applications in the left part of the slide. So this is actually what is doing Arcuda. Arcuda, which stands from Remote CUDA, is a software technology that enables a more flexible use of GPUs in computing facilities. How Arcuda is doing that? How Arcuda is adding this flexibility? By enabling sharing the GPUs among different applications, regardless of these applications are run in a node with or without a GPU. Okay, so how it actually works. So remember that before we have mentioned that we have an application and it's using CUDA libraries. So what we are actually doing inside our CUDA is, okay, we have the client side and the server side. In the client side, in the left part of the slide, we can see that the application is running as usual. But when this application calls a function from the CUDA API, our CUDA client intercepts that function and forwards it through the network to the server side. In the server side, we have a node which actually has a GPU installed. So in this case, what happens is that the Arcuda server receives this request and actually runs it on the physical hardware, on the physical GPU. And then once this operation is executed, it just forwards the results back to the client through the network. And then the results are service to the final application, to the original application. So if you remember, I showed you at the beginning some code for running a CUDA program. So when we want to use, this was the code that we needed to use when we were using CUDA. When we want to use, we want to use Arcuda, the program is actually the same. So we don't need to change anything. The only change we need to do is that instead of linking the application against the original CUDA library, we just need to use the Arcuda library. So if we have originally compiled the application using dynamic linking, we don't need to do anything. We don't need even to recompile it. We will just substitute the CUDA library by the Arcuda one, and that's all. Okay, so great. So now let's see how we move now that we have remote GPU virtualization. So in the beginning, we have seen a cluster which were interconnected by a network in which all the nodes were basically replicated with a couple of CPUs and one GPU. Okay, this was the physical configuration. But now, thanks to this virtualization software, what happens is that we could see that all the GPUs are available to all the nodes in the cluster. So logically, we will have like a pool of GPUs. I'm referring to the image at the bottom right of the slide. So we can see that now we have different nodes interconnected by a network, but now virtually, logically, they can access to all the GPUs in the cluster. Okay, so we have moved from the physical configuration at the top left. At the top, we have moved from the physical configuration that we can see in the top left of the slide to the logical configuration that we can see in the top right of the slide, just by adding a middleware, the Arcuda middleware, just by adding a software layer. Okay, there are different remote GPU virtualization frameworks. The one we are commenting today is called Arcuda, as we have mentioned. There are other efforts like gVirtus, DSCUDA, vCUDA, and other efforts. Some of them are publicly available, other not. Some of them are obsolete. Anyway, we are in this tutorial, we are focusing on Arcuda. Okay, let's see now some performance results. So for instance, here we are showing memory copies from host memory to GPU memory and vice versa when using patchable memory and pin memory. We have here a comparison between the original CUDA and the publicly available remote GPU virtualization frameworks. In this case, we can see that we have original CUDA in green, and then we have the dashed blue line refers to Arcuda, the dashed red line refers to JVirtuos, and the violet line refers to DSCUDA. In the case of patchable memory, we could see that Arcuda, in this case, obtains better bandwidth even than CUDA. And in the case of pin memory, we were not able to run the test for DSCUDA because it seems they don't support pin memory. But for the rest of the frameworks, so CUDA is the best one in this case, and then follow by Arcuda and then JVirtuos. Okay. So these tests were run using an InfiniBand network, FDR, and with a K20 GPU. So now that we have seen what is Arcuda and what is remote GPU virtualization, is this actually useful? So the first question one of the questions we have seen in the introduction is that some of the features that the GPUs were missing were that it was not easy to share GPUs between the nodes in the cluster, and we have seen also that if we want to aggregate a lot of GPUs in a single box, so we have some limitations. So let's focus first on the first feature, which is the number of GPUs in a single box. So for instance, when we are not using Arcuda and when we are not using any other techniques such as MPI, only the CPUs in one node can use the GPUs in that node, installed in that node. For instance, in this image, we have 2 CPUs in node 1 and 1 GPU. So only the 2 CPUs of node 1 will be able to use the GPU in node 1. Okay, so if we would like to put more GPUs in one box, in one server, in one node of the cluster, this will allow us to increase the computing power of that server or box, but we are limited. We are limited in space. We don't have infinite space in the box. We can be also limited because that server doesn't have PCI Express available or things like that. So we have space limitations and we have also technology limitations among others. Okay, so we could have different problems that do not allow us to put more GPUs in a server node. So we can see here that if we don't have anything, hardware or software addressing this problem, and if only the CPUs in node 1 can use the GPU in node 1, then if we are running a regular CPU application in node 1, let's say, and this application is not using the GPU, so the GPU will be idle. And even more, if we would like to use from node 1 all the GPUs in the cluster because we are running a very compute intensive application, the rest of the GPUs will be not be accessible to node 1 because we don't have anything to make these applications to make this application access to those GPUs. So we are showing here, for instance, how we have using Arcuda, how we have enhanced a multi-GPU application. In this case, we had a box with 4 GPUs, and in green, the green bars, we can see the results for CUDA. We were able to run up to 4 GPUs because we only had a physical GPU with 4 GPU, a physical server with four physical GPUs. Notice, however, that if we use Arcuda, we are able to use not only the 4 GPUs in that server, but also all the GPUs in the cluster. In this case, we have in the cluster at our university, at that point in time, we have 14 K20 GPUs in different nodes and connected by an FDR InfiniBand network. So then we were able to run this application with more than 4 GPUs by using Arcuda. And as you can see, in this case, this application scales very well. And by adding more GPUs, we reduce the computation time. So this was a way, by using Arcuda, by using remote GPU virtualization, this was a mechanism to add more GPUs to one application in a virtual way. Another work in progress that we have is, for instance, using Blender. If we want to renderize an image, we can do this using multiple GPUs. In this case, the image can be divided in regions, and each region can be renderized by a different GPU. If we are limited to the GPUs in a box, we can do it only with 1, 2, 3, 4, the number of GPUs we have in the box. But if we can use all the GPUs in the cluster, such as in this case, so we can use up to 16 GPUs, because in the cluster at that moment in time we had 16 GPUs, and again the execution time is reduced by using more GPUs. In this slide, we just show that we had access to one cluster which has a lot of GPUs, and we just ran a device query just to show that we were able to have access to a huge number of GPUs. And here the only problem is that we need an application which scales well in order to make use of these 64 GPUs. Okay, so I think this will be related to the first concern, okay, related to how to put more GPUs in a single box, or how to make available many GPUs to a single application by using virtual GPUs. If you want, we can do the first coffee break here, and later, after the coffee break, we start with the second concern. Okay. So if you want, we can have a coffee break of, let's say, 15 minutes, and we meet here again. So I'm just writing in the chat that we have a coffee break now. And we see you in 15 minutes. My current time is 10 to 4 p.m. So here in my current time, we'll see at 4 and 5 minutes. I don't know what is your current time, but yes. So see you then in 15 minutes. Okay. Many thanks. I will stop, by the way, the recording, and see you. See you soon. Enjoy your coffee break.
This meeting is being recorded.
Okay, so welcome back. I hope you have enjoyed your coffee break. So As we have mentioned before, the first concern was about having more than one GPU in a server. We have commented that usually we have some limitations when we want to add more than one GPU in a server. So currently, I think there are servers with up to 8 GPUs, but that's not usual. The usual thing is that we have 1, 2, or 4 GPUs in a server, and if we want to use more GPUs, we have more difficulties in order to have such a server. So we have seen that one way in which remote GPU virtualization could be useful is precisely that, in being able to use more than one GPUs from one server by sharing the GPUs of other servers. The second concern that we are showing in this presentation is also related with sharing the GPUs in different nodes. So, for instance, here we see that if we have a regular server without using remote GPU virtualization, all the nodes that only run CPU applications have their GPUs idle. Those GPUs are not being used. So these GPUs we have seen before that they are consuming some energy and things like that. But if the applications that are running on those nodes are only CPU applications, those GPUs are not used. So if we can share, if we will able of sharing those GPUs among other nodes which are actually using GPU accelerated applications, that will be a way in which we can make even better the use of GPUs by using remote GPU virtualization, by using Arcuda. So why we should be interested in sharing GPUs among other applications? So as we have seen in the beginning, not all applications utilize the GPU 100% at one. Do not utilize the GPU at 100%. There are some applications which only use the GPU the 20% or something like that. In that case, it seems something. It seems a good idea sharing the GPU application between different the GPU between different applications. Okay. So, for instance, let me show you more results showing this. So, in this case, we have a workload of different applications, and we can see the normalized workload execution time in the green bar. And we can see in terms of the time in which the GPU is allocated to this workload, and we can see in orange the actual utilization of the GPU. As you can see, for the different workloads we have, the actual GPU utilization is very low. The time in which the GPU is allocated to an application is higher, but it's also not all the time. There is some space in which the GPU is even not allocated at all. So this shows us that it will be, in this case, in this scenario, in the case of these workloads, a good idea to share GPUs. Of course, there will be other workloads in which the GPUs are utilized 100% of the time, and maybe it's not a good idea, but in some cases it could be a good idea. So what we are proposing here is precisely using remote GPU virtualization to address this concern. Okay, so in summary, what we have seen here is we have highlighted a couple of concerns that we have right now that we think that in which we think GPU virtualization, remote GPU virtualization can help. And the first one was we have a multi-GPU application. By using remote GPU virtualization, we can provide that application more GPUs in an easy way than the physical number of GPUs that we have installed in the server. And the second point will be that in case a node is not using a GPU, we can share that GPU with another node, with another server, which could need that GPU. Okay, so if we progress in this idea of having many GPUs in a single box, so what we are mentioning here is that assuming the scenario we are commenting during this presentation, in which we have an interconnection layer with different nodes, and each node has one GPU. For instance, if we are running a multi-GPU application in node 1, this application will be able to access, thanks to remote GPU virtualization, to the GPUs in node 2, in node 3, in node n. This actually will be like having a virtual GPU. Okay, so in this case, if we have n nodes, each one with one GPU, in the end, we will be able to have per node n virtual GPUs. Okay, one will be the physical GPU of that node, and the rest will be the remote GPU virtual GPUs from the rest of the server. Okay. Okay, so let's say that we have managed to address the previous concerns. Now we can use from one single box, we can use a lot of GPUs in thanks to remote GPU virtualization, and now we can also share those GPUs among different nodes in the cluster. What about the performance? It's going to be the same performance using a physical local GPU than using a remote virtual GPU. So let's say we are going to see some numbers now. Previously, we have seen some performance results. Now we are going to see more performance results. First of all, one of the most important things when we are using GPUs to accelerate applications is that, as we have mentioned in the beginning, in the snippet of the code we have shown, we need to copy data from host memory to the GPU memory. Then we need to process to do the computations in the GPU memory, and then we need also to copy back the results to the host memory. This is the usual way. Okay, so this means that in CUDA we have one physical node with one GPU, and we copy from the host memory to the GPU memory. Okay, and in the case of remote GPU virtualization, in the case of ARCUDA, what we are doing is, okay, we have one node, and we need to copy from the CPU memory. We go through the network and we copy to the GPU memory of the remote server, which is offering the GPU. Okay, so memory copies go in both directions. As we have mentioned, we copy from host memory to the GPU memory. We perform some computations in the GPU, and then we copy the data back. There are two flavors of these copies. In both directions, we can use pin or either pin or patchable host memory. At the time we did the performance analysis we are going to show, most of the applications used patchable memory. Okay, so for instance, here we are showing the performance of copies through the network, and we are comparing it to regular CUDA. Okay, so first of all, we have run this experiment with CUDA and different GPUs. We have a K40 GPU, a P100, and a V100. Okay, and we are showing here the results for memory copies from CPU memory, host memory to GPU memory at the top left of the slide, and we can also see the other direction from GPU memory to host memory at the top right of the slide. When we add in this performance analysis the results from CUDA, so the CUDA results, not using virtualization, using a physical GPU are in red. The CUDA results using remote GPU virtualization are in red. So CUDA, original CUDA in green, remote GPU virtualization are CUDA in red. We can see here that we have more or less similar results. In this case, at the bottom right of the figure, we can see that in the case of the V100, in this case, the performance difference is higher. And as you can see, as new in the case of CUDA, as new GPUs appear, our performance were going down. So we started a research here and see, okay, why when we have a newer GPU, the performance is worse than the previous generation. So, and we detected that there were something not working very well in the internal architecture. So after that, we did a new, we improved the communication layer of CUDA, and you can see the new results in blue. So in this case, you can see that CUDA performs better in all the cases than CUDA. And yes, so in terms of memory copies, then there is no performance loss when we use a remote GPU virtualization. Of course, in this case, this performance is thanks is because we are using a high performance network. If we only have a regular network, Ethernet network with 1 gigabit, so the performance, of course, will be lower. But in this case, if we are in an HPC environment using an HPC cluster, we can assume that we will have a high performance network. Okay. Then the next case is when we have multiple GPUs. So in the case of CUDA, of original CUDA, at the left side of the slide, we can see that we have a node with a couple of GPUs, okay, with 2 GPUs. In this case, if we want to copy from memory of GPU 1 to memory of GPU 2, we go, in this case, through the PCI Express, and we perform the copy. In the case of CUDA, at the right of the slide, we have 2 scenarios. In one scenario, we are running the application in one node, and then we are using 2 GPUs which are physically installed in the same node, remote node. So in this case, the GPU memory copy will be done in the same case as in the CUDA scenario. But if we move to another scenario at the bottom right of the slide, we have one application running in one node, and this application is using 2 GPUs. Each one is installed in a different node. So in this case, what we need to do is the memory is going to be copied from the GPU 1 in the node 1 to, let's say, the GPU 2 in a second node. So in this case, the copy between GPUs is going to be also done through the network. So in this case here, we are showing the copies between GPUs from GPU to GPU. Okay, and we can see here that again we have very good results, and there is no performance loss when we compare to CUDA. Okay, so we have seen the performance regarding memory copies. Performance when copying from host memory to GPU memory and from GPU memory to GPU memory. What happens actually with the performance of applications? Because the performance is not only measured with bandwidth, the applications are also doing some computations. So what happens when we include, apart from the memory copies, the computations? So in this case, we are showing several examples with different applications. We are showing a comparison of Arcuda compared with CUDA. Here we are showing two flavors for Arcuda. In green, we have Arcuda using an EDR InfiniBand network and a K40 GPU, and in blue we have an FDR InfiniBand network with K20 GPUs. So as you could see here, some applications, for instance, the GPU lib SVM, we have when using FDR a higher overhead, when using EDR a lower overhead. This probably means that this application is more memory bandwidth and more memory bonded. Bandwidth bonded. So it's doing a lot of transfers, and in this case, when we have a better network such as EDR, it performs better than when having an FDR network. And we can see also some cases in which the overhead is negative. This means that Arcuda runs faster than regular Arcuda. Remember that this could be related to the fact that we have seen before that in some cases Arcuda was faster in performing the memory copies. Okay, here we can also see another comparison, comparing also the times with CUDA. We can see here the not only the overhead but the actual execution time, and we can see here the times in seconds. So you can see here that some applications in the left side of the figure, these applications, the execution time is from 10 seconds to 70 seconds, and on the right side we have applications which take longer, which are up to over 400 seconds. Okay, so this in terms of performance. Now here we are showing performance also with a more recent GPU, which is the P100. And again, we see that, for instance, for these two applications, we see that we have very good results. So the performance is more or less the same as using a remote, is more or less the same as using a local GPU. And in some cases we have that we run even better, such as in this case. Okay, so yeah, we have seen that. Then in terms of performance, we can get a similar performance than a local GPU when using a remote virtual GPU. Okay, so are there more benefits of using remote GPU virtualization, of using Arcuda? Let's see more benefits. For instance, one benefit will be when using virtual machines. If we want to use a GPU in a virtual machine, we usually need to use the PCI pass-through technique, which only allows us to assign exclusively the physical GPU to one virtual GPU. It is not possible to concurrently use the GPU by different virtual machines. So what we can do, thanks to remote GPU virtualization in this case, is by only adding this software layer or this middleware layer. So we can have two scenarios for sharing these GPUs. In the case we have a high performance network available, such as the InfiniBand, we can have an InfiniBand physical function of this network, and we can create virtual functions of this network adapter. And thanks to those virtual functions, we can assign each of these virtual functions using PCI Express pass-through to the virtual machine. And by doing this, we can then actually go through the physical network to the remote server hosting the physical GPU. And by doing this, we will be able to concurrently share a remote GPU among the different virtual machines in the original node without concurrently sharing concurrently sharing the GPUs. In the case we are in a low performance network, what we can do is we can put the Arcuda server in the host Linux in the host operating system of the virtual machine, and the guest operating systems will have the Arcuda client running, and thanks to that we will be also able to share one physical GPU concurrently among the different nodes of the cluster. Notice that currently NVIDIA has also released the MIG, the multi-instance GPU, which also allows you to share virtual GPUs. But in this case, that feature is only available in the latest GPUs. What happens if your cluster doesn't have this latest GPU? So in this case, Arcuda still will be useful. Some performance results. So here we are showing a graphic, a figure in which we see the comparison when we use CUDA using a virtual machine and with the technique of pass-through. Then we show Arcuda, the performance when not using a virtual machine. Then we have Arcuda when using virtual machine, and the scenario in which we have a high performance network and we have an InfiniBand network adapter, and we have done this thing of creating virtual functions of this network interface and assigning that function, virtual function of the network interface, thanks to pass through to the virtual machine. And finally, we have also in black color, in the black bars, we have the Arcuda scenario when using a virtual machine, and in this case, using the local network adapter to access the GPU in a virtual way. And we can see here some performance results. We can see here the overhead. We can see that when we use the Arcuda with the InfiniBand network adapter doing the virtual functions, and for each virtual function we assign this virtual function of the network adapter to a virtual machine using the pass-through, we see here that we have the best results, and the performance is not similar to the CUDA one. Okay, another way in which we can enhance our cluster by using Arcuda is, for instance, server consolidation. So we could assume that we have, let's say, 14 nodes in one cluster at the left side of the image of the slide, and we see here that we have for each node we have different amount of GPU utilization. So we could think that maybe we can consolidate some of these servers, switch off those servers, and migrate the GPU tasks to other servers in order to have more GPU utilization in the nodes which are switched on, and consolidate servers and switch off those servers in order to save energy. So in this case, what we need to do is, for instance, in the node 2, we are migrating all the tasks in this node to another node in order to switch off this node. And we do the same with the rest of the nodes. And in the end, we have some nodes switch off at the right side of the slide, and the nodes which are switched on has a higher GPU utilization. How this consolidation process works. So we have, let's say we have a scenario like in the left side of the slide. So we have four nodes, and let's say that those nodes are running an application, and what we at a certain time, let's say that one of these nodes is going to switch off. So the scheduler decides this node, that node is going to switch off. So all the applications running in that node are migrated to another node, and finally this node is switched off. For instance, in the case of this application that we are showing here, we see that we have the memory occupation or memory utilization in the green, in the yellow bars, and in red we have the GPU utilization. Okay, so we see that on average in the dashed green line we have 40% of GPU utilization. What happens when we migrate? For instance, let's say that in the beginning both nodes were running the same application, and at some point we migrate from one node to the other, from the source node to the target node, the application. So at that point the source node will be switched off, and the target node will be running two instances of the application it was running in the beginning and the migrated application. As we can see, this actually increases the GPU utilization, also increases the memory utilization in the target node, and also increases the average GPU utilization. In the lower part of the slide, we can also see the power consumption, and we can see that in this case, of course, the power consumption is going to increase a little, but in the end, if you remember, one instance of this application took near 200 seconds, and in this case, after the migration, you see the two instances only take 225 seconds. So we are actually probably saving energy. Okay. So in order to better reflect this, the overhead of migrating, in this case we have done several migrations. So we have migrating from one node to another, then perform another migration to another node, a third migration, a fourth, just to see what was the overhead of doing those migrations. So in this case, when using InfiniBand networks, you could see that the overhead was very, very low. Another way of benefiting from remote GPU utilization could be in the case in which we have a very heterogeneous cluster. For instance, we have x86 nodes, we have ARM nodes, we have also IBM Power nodes. So in this case, from all these nodes, we will be able to use remote GPUs, which could also be hosted in nodes with different architectures, and everything will be transparent to the user thanks to Arcuda. So it will be possible to mix all these kind of architectures in order to use remote GPU virtualization. This could be also a way of benefiting from Arcuda. Okay, so what is the current status and the near-term roadmap of Arcuda in terms of releases and so on? So we are only showing here releases from 2016. So at that point in time, in 2016, the Arcuda release was focused only on HPC applications. It had very good performance, but it still does not support schedulers such as SLARM, and it only provided initial migration support. After that, in 2018, we introduced the support for deep learning frameworks and also renderers. We improved also the support for HPC applications, and still we didn't have support for schedulers or migration. Then we improved that version with bug fixing, and then in later, 2 years later, in 2022, we have we improved the communication layer, which are the results I have shown you also in this presentation. We also improved the support to HPC and deep learning and the renderers. We also added support for containers, for the SLARM scheduler, and the migration support was not yet introduced, but we hope it will be introduced in future releases. Later that year, in 2020, we also released another version with some bug fixing, and right now we expect to release a new version soon with support for CUDA 11, multi-tenancy, also including very useful tools such something similar to the NVIDIA SMI tool, but in this case for remote virtual GPUs. We hope also to include in this new release a new Arcuda GPU scheduler, and also additional bug fixing and things like that. This will be as soon as possible, but we cannot say a date right now. Okay, so we will mention this in the hands-on session, but Arcuda is freely available. You can get a free copy of Arcuda in the website you can see in this link, arcuda.net. You can also follow us on Twitter. And yeah, so this is the end of the first part of the tutorial. I don't know if you have any question. You can always email your questions through the support that you can see in the Arcuda website, and you can also write your questions in the chat if you want. So with this, we finish the first part of the tutorial, and now we can move to the second part of the tutorial, which is actually the hands-on session. Let me change the slideshow. Okay, hopefully you can see my slides now. So right now we are going to start the hands-on session. I don't see any questions in the chat. So we will introduce this session and probably we'll do another coffee break before actually starting connecting to the servers and doing the actual hands-on. Okay, so right now, hopefully you will know what is Arcuda, but we will just make another attempt to make sure that you actually know what is Arcuda, and then we will see how to install and use Arcuda. We will see how to use Arcuda over HPC networks in case you have one. We will focus on InfiniBand networks. Then we will show some sample scenarios on how it could be possible to take benefit from Arcuda. And if you have any questions, we will be able to solve them at the end of the hands-on session. Okay, so what is Arcuda? Hopefully right now you already know this, but just in case. So with the original CUDA, we have an application running in one node, and this application is being accelerated by a local GPU. When we move to the Arcuda scenario, to the remote CUDA scenario, the application is running in one node, but in this case, it's using a remote GPU located in another node in order to be accelerated. Okay. So what do we need to do to install and use Arcuda? So first of all, we need to have CUDA installed in the node which is going to be the server, in the node which is actually has the GPU, and the node which is going to serve the GPU request. We need, of course, to have a communication between the node which is going to run the client application and the node which is hosting the GPU, the server. For installing CUDA, you just need to go to NVIDIA website and install it, follow the instructions. For client and server communications, you can use either Ethernet with TCP/IP based communications, or in case you have a high performance network such as InfiniBand, you can use RDMA based communications. Okay, where can we obtain Arcuda? So you just need to go to the website arcuda.net, and then you click on the software request form, you fill that form, and you will receive a copy of the software. This software, the package, contains different folders. One of the more important are the documentation folder, which includes the Arcuda user guide and also a quick start guide. We have also a binary folder, which includes the Arcuda server daemon and the license server daemon. Then we have a configuration folder, which includes the Arcuda license configuration file. We will comment this later. And we have also the library folder, which includes the Arcuda library. Remember, we have mentioned in the first part of the tutorial that in order to use Arcuda, we need to change the library, which is linked against the library link with the application. So instead of using the CUDA library, we need to link the client application with the Arcuda library. So in this folder is this library. And installing the Arcuda software is just untarring decompressing this tarball in both the servers and the client nodes and starting to use it. Okay. If you want, before we continue with actually logging to the servers and running actually this a live demo, we are going to do another coffee break. So, and by this I can prepare all the notes, and we start here in, let's say, 15 minutes. Okay. So I'm going to stop the recording now, and I'm going to type in the chat that we are going to do another coffee break, and see you later. Okay, enjoy your coffee break, and thank you very much for your attention. See you later. Bye.
This meeting is being recorded.
Okay, so before the coffee break, we have just mentioned that you just need to go to the Arcuda.net website and request for the software. We have mentioned what you will receive in the software, in the package contents. And we have mentioned also how to install Arcuda. So we are going to see now how to actually configure it once we have received the package content and we have decompressed it in both the servers and the client nodes. So the first thing we need to do is we need to start the license server, which is basically a server with the license we have provided you. For doing this, you just need to introduce in the Arcuda config file the server, the license key you have received, and the IP address or the name of the server where the license server is running, and run the license server. So we are going to see how to do this. So let me just keep these terminals alive. So here we just need to start the license servers. So you need to go to the folder, to the path where you have decompressed the CUDA software. You just run this command, which stands for Arcuda license servers. You are going to run it in interactive mode and verbose mode. If we don't put the options I and B, it will just be a diamond running on background. Okay, but I'm running this. You will see now because I wanted to show you what happens. Okay, so what you need to do actually is just run it. When you run it in the beginning, you don't have the correct license, so you just need to copy this error and submit it to this email address, and you will receive a proper license key. And after that, you just need to copy this license key into the proper configuration folder, and with that you will have the license server up and running. I'm going to skip this because this is a cluster which is shared among different people, and the license server is also currently running, so I don't need to run this. But in your case, you just need to do this. Go to the bin folder from the Arcuda package, run the license server, send the error to the support, and you will receive the key. Okay, so once we have the license server up and running, we need to run the actual Arcuda server. So in this case, we need to run the Arcuda server in a node in which we have a physical GPU installed. Okay, so this Arcuda server is going to be run as if it was a CUDA program. So for that, we need to export the path to the CUDA binaries, like we do with a normal CUDA application, and we need to also include the path to the CUDA libraries, because it's going to be a CUDA application which is going to be run using the CUDA libraries. And then we go to the folder where we have decompressed the Arcuda software, and we run the server diamond. Again, we can use the options interactive and verbose to make this to have additional information. Okay, let me check if I have. Okay, everything is correct, I think. So now I'm going to keep alive all these terminals, and now I'm going to run the server. So again, we just export the path to the CUDA binaries. We export the path to the we include the library in the library path, the path to the CUDA libraries. And we go again to the path where we have decompressed the Arcuda software, and we just execute the diamond, the Arcuda diamond. We start the Arcuda server in interactive and verbose mode. Hopefully this will run. Okay, and you will see here that it tries to connect to the license server. In this case, it was previously started in this machine and is connected to the license servers, and it tells us that the license is valid and we could continue. Okay, so now that we have the server started, we are going to run a CUDA program, but using a virtual GPU. Okay, so in the end, what we are doing is we are going to run a CUDA program in this node, and we are going to use a remote GPU located in a remote node. Okay, so for the client, what we need to do is we need to set the environment variables as follow. For the path, we have the path to the CUDA binaries. But for the library, instead of using the CUDA library, this is very important, we need to include the Arcuda libraries. Depending on where we have decompressed the Arcuda software, this path will change. Then we need to tell Arcuda how many GPUs, remote GPUs we are going to use. In this case, we will be using one, so we export the environment variable name as Arcuda device count, and we say that we want to use one remote GPU. And then after that, we need to say, we need to specify Arcuda to indicate where this GPU is located. In this case, we say, okay, Arcuda device 0 is located in this server name or this IP address, and inside that server name or IP address, it's the GPU number 0, 1, 2, whatever. And after that, very important, if our CUDA application was not compiled using dynamic libraries, we need to do so. We need to compile this application using dynamic libraries. For that, in the case of the NVIDIA CUDA samples, we need to include the flags, the following flags to the NVIDIA CUDA compiler: CUDA RT equal cert. Okay, this is very important. Okay, adding these flags to the compiler, and finally we just run the CUDA program as usual. Okay, so let's try this. Let me just keep alive those terminals. Okay, so the server is running, and now what we are going to do is running one client application. We just export the path to the CUDA binaries. We then include, very important, the path to the Arcuda library, not the CUDA one, the Arcuda library. In this case, we have the Arcuda library in this path here. Okay, so we just export this, include this path in the library path. Then we say, okay, in this case, we are going to have access to one remote GPU. So the device count is 1. This remote GPU is located in a server which has this IP address, and inside that server, the GPU is the GPU number 0. And we just run the application as we do normally. Okay, so we just run this and start doing. This is just a device query. It just query the device property of the GPU in the server. So in this case, it has connected to the server and it has indicated that the remote GPU is a Tesla K40. In this case, if we go to the server, we see, okay, we have a new connection established with this node. This is the client where the client application is running, and it's receiving all the applications. Is using that. This is also saying us that we are using a TCP connection, etc., and that the application has finished. Perfect. Now we are going to run a bandwidth test. A bandwidth test is just a test included in the NVIDIA SDK, which is just doing memory copies from host to device and also from device to host. If we move to the server tab, you see that here we are receiving the CUDA and copy operations from the client application. Okay. So now it has finished the copies from host to device, and now the copies from device to host are starting. As mentioned, we are using TCP/IP network. In this case, is 1 gigabit Ethernet network. And as you can see now, one of the concerns is that this is a bit slow, right? The performance with this very low bandwidth will not be very good, right? So what can we do? So in this case, we are using, as I have mentioned, TCP/IP protocol in our cluster. Apart from this TCP/IP, this Ethernet network, we have also InfiniBand network. So in this case, we can, instead of using that network, Arcuda has a communication layer that allows to that offers improved communications over InfiniBand networks. So we could do is just using that network actually. Okay. What we need to do to use that network? For the server is the same. We don't need to do anything special, right? The only change is for the client. In the client, we need to specify to the client, okay, instead of using the TCP protocol, we want to use the InfiniBand protocol. So let's do that. Our server is still up and running. I'm going to keep this alive. And we go again to the client. And in this case, we are going to run the application, but using InfiniBand. As mentioned, we just need to export the environment variable Arcuda network and mention to Arcuda that, okay, indicate to Arcuda that, okay, we want to use the InfiniBand network. Then we just go to the same example we were using before, the device query example, and we run it. And well, the result is the same, but if we come here, now we see that actually we are using the InfiniBand connection. Before we were using TCP, remember that we were using TCP connection, but now we are using InfiniBand connection. And okay, the remote server is the same one. If we run now the bandwidth test, the same that we have run before, now it will be faster because we are using a faster network. In this case, you could see that the performance is much higher, and this has finished in very, very quickly, actually. Okay. Okay, so now we have the problem solved. We have we are able to do memory copies thanks to this high performance network. We have a bandwidth comparable to the CUDA one. So so great. The bandwidth is no more a problem. Okay, so now that we have installed and configured Arcuda, how could we take benefit from this middleware. For instance, we are showing here some scenarios. The typical behavior of a good application is we just move data from the host memory to the GPU memory. We do a lot of computations there to compensate the overhead of having moved this data to the GPU, and then we move the data, the results, back to the host. Well, this actually benefits very well Arcuda. This behavior fits very well in the Arcuda approach, because the more computations we do in the GPU, the less overhead we will have with Arcuda, because the extra overhead of having moved the data through the network will be compensated by this time spent in computations. We can see, we can divide the applications. Well, this is just an approach. There could be other approach to divide the types of applications. We could say that application is bandwidth bounded if there are more transfers than computations. In this case, the Arcuda overhead will be higher, because if we are only moving data through the network, the overhead is going to be higher. On the other side, we have a compute bounded application. In this case, there will be more computations than transfers, much more computations than transfers. And as I have mentioned, this will imply less Arcuda overhead, because all the overhead of moving the data through the network will be compensated by this high amount of computation. And then we have, let's say, an intermediate type of application, which is not bandwidth bounded and not compute bounded, is in the middle. In this case, depending on the application, it will perform well or not so well with Arcuda. Okay, let's see, for instance, the performance when we do a matrix multiplication with CUDA and Arcuda. For instance, let me keep alive those terminals, because if I don't do nothing, they will switch off. So in this case, we are just running a matrix multiplication with, first we are going to do this with Arcuda. It's just a matrix multiplication test, okay? So we are going to run this with Arcuda. And we have here this amount of time for different dimensions. We are not going, we don't want a very time-consuming test in order to make this live demonstration move more dynamic. So we see here different dimensions for the matrix mul and different times. And I'm going to run actually the same, but in this case using CUDA. Okay, for using CUDA, remember that from this client application we are using the GPU located in in a remote server, which is located in this tab. Okay, so what I'm going to do is I'm going to stop this server. I'm going to clear the screen. And instead of using the Arcuda, I'm going to run here in the server, in the same place where we have been running the application from the client side. But in this case, I'm going to run it using the CUDA application, right? So in this case, I'm going to run the same test I have just run with Arcuda, but with CUDA, with the a local GPU, with native CUDA. We go to the same path, we run the same command, and so as you could see here, okay, if we compare times here, this is CUDA and this is Arcuda. When we are working with lower matrix dimension, the time is a bit higher with Arcuda. But yes, for larger matrix dimensions, the times are very, very similar, as you could see. Okay. Yeah, the times are very similar. So this means that the performance when we are running this matrix multiplication comparing CUDA and Arcuda is more or less the same. But to be fair, should we compare Arcuda with CUDA? Because what is actually happening is that in this in the client where the client application is running, we don't have a GPU. So we were able to run this test using a remote GPU thanks to Arcuda. But if we don't have Arcuda or any other remote GPU virtualization framework, what we have are CPUs. So perhaps, to be fair, we need to compare these results with running the. We need to compare those results to running the application with the CPU. So let me do that. I'm going to start the Arcuda server again. I'm going to need this for later. Okay. Do the same thing that happened before. Okay, the server is started. And now, as mentioned, what I'm going to do is run the same test, but in this case with the CPU. So we have run the matrix multiplication with Arcuda. We have seen that the results, the performance is very similar to CUDA, and we are going to run it with only CPU because in this node, we only have a CPU. We were using a virtual GPU, but if we don't have Arcuda, we will only be able to use a CPU. So we keep in mind these numbers because they are going to be removed from the screen now. Okay, let's just focus on the last one, perhaps, which it was 11. Okay, for the higher matrix dimension. Let me keep alive this terminal. Okay, so what we are going to do here is actually running the same test, but only using CPU. So we run the same test. And you see, before here we have only 11, and now we have 131. Well, we are just using the CPU. So, of course, if we compare a local GPU with a remote GPU, the performance is not going to be could be a bit worse. But if we compare a CPU against using a remote GPU, the performance is going to be very good when using. Is going to be much better when using the remote GPU. Okay, great. So we have demonstrating this sample scenario for taking benefit of Arcuda, in which we compare the results from a GPU to a remote GPU and also to the local CPU. Okay, yeah, this is what we have actually done. We have seen that it's better in this case to use a remote GPU than a local CPU. Okay. Another sample scenario could be adding more GPUs. Imagine that my application is able to use multiple GPUs and it scales well. So the more GPUs I have, the less execution time I have. With Arcuda, I can easily add more GPUs because I can use all the GPUs in the cluster. In this case, what I'm going to do is, remember I have one application, one server started here. I'm going to start a second server here. Okay. So this is another server. In this case, I would like also to highlight, in this case, this new server, let's say that you could imagine this is a new server that we have just added and it has newer GPUs. So this could be also a potential benefit from Arcuda. Imagine that you have a legacy cluster and then you attach a new box with new GPUs, then all the nodes in the cluster will be able to use this newer cluster with the new GPUs. Okay, then. So yes, let me keep alive this terminals. So I have one server here, I have a second server here, and now in the client application, I'm just going to run a very simple device query just to show you that now I have access to more GPUs. What I need to do to add more GPUs? So actually, this is the CUDA scenario will be this. You have one node and all the GPUs you have installed in this node. And with Arcuda, you can access GPUs not only in one node, but in all the nodes accessible from your network. Okay. So, and for doing this, we just need to do, in this case, we need to indicate the number of remote GPUs. Before, we were just telling that we were going to use one GPU. In this case, for instance, we are going to say we want to use 5 GPUs, and we say that GPU 0 and 1 are both in node 1, and inside node 1, the GPU 0 is in device 0, and the GPU 1 is in device 1, and then we could assign devices from other nodes. For instance, here we are saying that the second GPU is in the in node 2, and the third one in node 3, and the fourth one in node 4, etc. Okay. And a tip here is, after doing this, just to be sure everything works fine, just check the configuration by running the device query, which is actually what we are going to do. Okay, we are going to run this device query with multiple GPUs. Okay, so in this case, we are going to use, we have 2 servers. The server we just started at the beginning, and the server we have just started. And in both servers there is one GPU. So we say, okay, the first GPU is in the server with this IP address and is in the device 0, and then the second device is in this server and is also in the device 0. So we run again the device query application, and this time we will see the 2 devices. Okay, so we have detected 2 GPUs, in this case the K40, which was allocated in the first server, and in here we have a big 100, for instance, which is the new server we have attached. And if you see here, we have a connection again, InfiniBand, from this node. Again, here we have a connection from this node. Okay, so both servers have received the connection, and this application has access now to 2 remote GPUs. If we had more servers, we will be able to add more remote GPUs. And in this case, if we have an application that actually is capable of taking benefit from more GPUs, this will be a very good scenario for using Arcuda. Okay, more sample scenarios. Heterogeneous clusters. This is not the case, because in our case, all the nodes we have right now are x86. But imagine that I have in the cluster different nodes with x86 architecture, power PCs, ARM PCs, etc. So then, thanks to Arcuda, we can access from one node, regardless of its architecture, to the GPUs located in a different node with a different or not architecture, and all of this will be transferred to the application, and thanks to Arcuda. Okay. So yeah, this is the end of this live demonstration. As mentioned, you can get a free copy of Arcuda at our website, arcuda.net. You can also follow us on Twitter. And yeah, if you have any question, I'm just going to move again here. I'm going to... Okay, and I'm going to see if we have actually any question. I don't know if we have any question. I don't see any question in the chat. As mentioned, you can email us if you have questions later. So this was what we have planned for today. We have also planned some time for the audience to
Can I ask something?
Let me share my screen, sorry. as you can see in the tentative schedule, we have planned for time to the audience to try Arcuda. But perhaps what we could do is you can just do your software request and try it on your own. This is take in mind that this tutorial was intended to be done in person, and in person has more sense having this extra time in order for the audience to test Arcuda, and us, the instructors, are there in order to help you. But in this case, and as everything is remotely, you can do this on your own, and you can request the software and let us know if you have any problem or any question. Yeah, so many thanks for your attention. Now, yes, is the end of my talk. Sure, Ihon, you can ask some questions. Yeah, I see that.
I mean, can you hear me?
Yeah, I can hear you.
Oh, okay, then I have some questions. So from my
Yeah, sure.
humble understanding, so
Yeah.
for using, if you want to use Arcuda, and if you already have original CUDA binary, I mean,
Yeah.
like already compiled host code plus the unmodified CUDA, the device code. I mean, not compiled, but the device code source. If I have those, then can I learn it without any modification to run on the Arcuda?
Yeah. Remember, if you remember, I'm going to show you the actual slide. Let me check. I have mentioned that you don't need to modify the source code, but what is important is that the source, the binary is compiled using dynamic linking. I'm going to show you the slide in which I have mentioned that. 1 second. So I'm going to share again. I think you can see my screen now, right?
Yeah, I can see it.
Yeah, so you see, you need to add to the NVIDIA CUDA compiler if you have not done this flag. So it's important that it is compiled using dynamic libraries, okay?
Yeah, that means that the already compiled CUDA program, the output binary will use the CUDA code with the dynamic linking, right?
Yeah, so if it is compiled using dynamic libraries and you add the Arcuda library, like in this slide, to the library path, then you don't need to modify your application. It will be transparent to you.
Okay. I have one more question. So,
Yeah.
you said this Arcuda can be used as like where there's like a multiple virtual machine and they can share the single like the graphic device within the host, right? Not directly pass through to the guest, right?
Yeah.
Yeah. In that case, also the guest, the program on the guest side code like doesn't need modification, right? That just only need like recompile, right?
Yeah, remember, it needs to be recompiled if it has not been compiled using dynamic linking. Okay, if it has been compiled using dynamic linking, you don't need even to recompile it. But yes, in the case,
if already compiled with the dynamic linking, then you don't even need to
do anything.
recompile, right?
It will.
Okay. What did you try to say?
No, yeah. I was going to say that you are right. You don't need to do anything else.
Okay, so then my last question is that to learn this, I mean, from my humble like understanding that when you try to learn this code, like this CUDA code with Arcuda link to the CUDA, if you are trying to learn on the guest inside the guest virtual machine, do those CUDA code, I mean, like a host program plus CUDA device code, will be like isolated among the like virtual machines. I mean, the host code will be using the only CPU resource to the virtual machine, and but at the same time, the CUDA code will use the host side GPU, right? That means then how does each individual virtual machine share the host, like a host device? I mean, is there a scheduler that like scheduling those each virtual machine's request?
Yeah, so in the current version, which is publicly available, what happens is the same as if you were running those two applications with CUDA in a single GPU. So imagine that you are in one host without virtual machines, and you run two applications. What happens? There is no scheduling. The applications just run, and they try both to use the GPU at the same time, right?
No.
Did you understand? I have explained it properly.
So you are like saying like if there's like just like a plain CUDA and only single host, if there's like a two application running on same device, then isn't it supposed to work, right?
So you can actually run two applications concurrently. The problem is that if you don't have any scheduler or any tool to make sure that the GPU is enough for running both applications, you cannot be sure if one of them is going to fail. But this is the same as with CUDA, right? If we are not extending that in that case. And this is
yeah, you can say it.
Yeah, this is as I have mentioned, for the publicly available version we have released. It's now publicly available. If you run an application from a virtual machine and another application from a different virtual machine, and both of them are sharing the GPU, there is no scheduling there. Both applications will be run. If they can run concurrently because there is enough memory, GPU memory, etc., perfect. If not, it will happen the same as with regular CUDA. If with CUDA you try to run two applications and there is not enough memory for both of them, well, one of them will not be able to run. So this will be the same with our CUDA.
Okay, so is there like a future plan that actually like isolate each individual resources? I mean, like each individual limitation of total memory to a single guest? Is there?
In future releases, you will be able to limit the memory allocated to each virtual machine, and with that, you will be able to solve the problem you are highlighting right now. Yeah.
Okay. Oh, that will be great. Okay. That was all my question. Thank you.
Yeah. Many thank you.
Okay.
Okay. So, any other questions from the audience? As I have mentioned, the meeting is being recorded, and we will make available the link for the recording as soon as possible. And yeah, as mentioned, the software is free, so just go to our website and request the software. Follow us on Twitter, and yeah, I don't know if there are not further questions. Many thanks for your attention. Many thanks for joining us today, and hope to see you soon. Hopefully in the next edition of the PPOP, and hopefully in person, physically in person. Okay. Many thanks, and see you soon. Bye bye. See you. Bye bye.
Okay. Thank you.